Hello friends, and welcome to another video. We're going to try and do the last run on our chemistry paper. I just hope I can be able to be fast enough to finish it. Alright, so again, just realized a few problems here. Of course, I didn't have all the time to listen to the rest of these videos before I posted them, but I spotted a bit of a situation here. Technically, what I wanted to say here, instead of what I wrote as splitting, the idea was to do what? To call it cracking. They call it cracking. So that's the word I was looking for, not splitting, but cracking. And in fact, to be on the safe side, because we are taking something out, so it's an elimination reaction. So maybe because the question is saying the type of the reaction, it's better to say elimination. But the name of the elimination reaction is cracking. So got a bit careless over there. Alright. And of course, for the requirements, if you need heat or some light, probably you could also add a catalyst here. Okay. Of course, you will have to know a bit of the theory there as to which ones are the possibilities, but I think they set conditions. They didn't specify exactly which ones, so I think that's fine. All right. So that was a bit of a nice question, and it was challenging. All right. So let's not waste too much time because we really don't have it now. I don't know. The power cuts are a bit friendly on us, so let's just keep working. Now question 5 says the reaction of 15 grams, that's the mass. So now you're dealing with stoichiometric calculations of an impure. Now this is impure, meaning it's not pure. Okay, not all of this 15 grams is going to be taking part in the reaction. Okay, of calcium carbonate, okay, with excess, so meaning this one will remain after the reaction is completed. That means the rate limiting reagent here is the calcium carbonate because it gets exhausted first. Then they're telling us that the concentration of our acid is 1,0, okay, it's just 1 mole per decimeter cubed, is used to investigate the rate of the reaction. So here it's a question on the reaction rate. Okay. You know that the reaction rate is affected by a few things: temperature, pressure, as well as concentration. Okay. Of course, even the phase in which these are, be it solid versus powder versus aqueous solutions. Now, okay, the balanced equation of the reaction, you know, they are very nice to you guys because, I mean, with us, we were given the names. You had to know how to write calcium carbonate as well as hydrochloric acid and do a balanced equation on your own. So you guys are very lucky. They make it easy for you. They give you all of this. So you know, when you combine a metal carbonate with an acid, you get 3 products, which is a salt, carbon dioxide, and water. So this is what you needed to know theoretically, and then you start working on balancing now depending on the charges that you're going to end up with. Okay, anyway, so they make it easy that 1 molecule of calcium carbonate reacts with 2 molecules of hydrochloric acid to produce 1 molecule of calcium chloride salt, 1 molecule of water, which is liquid, as well as 1 molecule of carbon dioxide in gaseous phase. Now it says the volume of carbon dioxide gas produced is measured at regular intervals. Okay, so this is the one that they are focusing on. So they are measuring the volume. A sketch graph representing the total volume of carbon dioxide gas produced as a function of time is shown. Now we can see here time 0 there was no carbon dioxide, T1 there was some carbon dioxide, T2 in fact there was an exponential rise in the volume of the carbon dioxide obtained, but then it started slowing down until it reached sort of that level, and we can almost tell that is the maximum volume at T3 because it just remains the same from there on. that means the reaction has stopped over there, or is so slow that it is insignificant what it produces. All right. Now, question which is easy, define the term reaction rate. Okay, easy. So no need to be losing marks on this one. So what are we answering here? We are answering question 5. So let's just do some movements here. See if we cannot press this one down. 5.1. So the reaction rate, basically, it is the, well, you can say that it is the rate of change of the concentrations of reactants, okay, let's just say of products and reactants, because whether you're focusing on the products, or maybe let's say and or, because you can't just combine the two. So this is the rate of change of the concentration of the products. That's what it is, because you're going to say the product over a particular time. So the more you're forming it, it tells you about how fast that reaction is. Or the rate of change of the reactants, by so much they are getting reduced, it also gives you the speed. So basically it is the change of the concentration of the reactants and products, or the rate of change of the concentrations of products and or reactants. Doesn't matter which one you choose to focus on. Okay, so I think that is 2 marks. Again, with these kinds of questions, you just need to make sure you understand. So the idea is change of concentrations, be it products and reactants. All right, so 5.2 says, now give a reason why the gradient of the graph decreases between T1 and T2. Of course, the reaction rate is slowing down, okay? Or some of the reactants are being used up, okay? So here you can just say the reaction rate is slowing down due to reactants being used up. Okay, not a big deal. Again, here you just need to have a bit of an understanding. You don't need too much to say there. Now 5.3 is asking, now changes in the graph between T1 and T2, so where there was this exponential rise over there. It says are due to temperature changes within the reaction mixture. Alright, so now it says, is the reaction exothermic or endothermic? Now there's a bit of a problem here, okay? There's a bit of a problem. So let's first focus on the gradient. What is the gradient? It is the change. According to this one, the gradient, we'll just write here, gradient equals the rate of change of volume over change in time, right? That's what we're getting. All right. So it gives us the rate of change. So which is basically what? The reaction rate, in essence, because that quotient is the reaction rate. Not a problem. So if we're talking about the reaction rate, so we can already tell here that there was an increase in the reaction rate, isn't it? Because in essence here we formed more of the carbon dioxide, so the gradient became steeper. So the steeper the gradient, it tells you the increment is the reaction rate. And this one, it's a positive gradient, so it means we are forming more of the products. Okay, so bit of mathematical integration here of gradients and how they work. So now if it was a negative gradient, it could be steeper, so that means it was decreasing, or maybe the reverse reaction. So this one tells us that we are favoring the forward reaction. Okay, not a problem. So let's have a look at this one and see. Now, what do we know about reactions? Now, the reaction, usually it has some A plus B going to maybe AB, okay? Now, basically, this, maybe let's just say XA, okay, let's not put too much pressure on ourselves. Remember, the reactants normally need energy to break bonds, right? So here you normally would be adding energy to break bonds, and then when you're forming new bonds, you release energy. So whenever products are formed, usually, in fact not even usually, they release energy. Whenever reactants are being broken down, you need energy to break those bonds, right? Because you need to break those intermolecular forces as well as you break the bonds so that new atoms can start to form new compounds. But now remember, in this type of reactions, we talk about the so-called enthalpic change. Is it enthalpic, enthalpy, or enthalpy? Enthalpy, okay. Delta H of a reaction. Remember, it tells us now if the reaction forms more of the energy than it uses energy. Normally what we have, that delta H is what? Is positive for the forward reaction, because we're going to release more energy than we are using, isn't it? And we know that if that is the case, if delta H is greater than 0, then it tells us that the forward reaction is going to be what? Well, if we release more than, hey, wait a minute, what am I saying now? Oh, sometimes this thing can be confusing way too. But if delta H is positive, it tells us that the forward reaction is endothermic, okay? Not a problem. And then if delta H is less than 0, it tells us that the forward reaction is exothermic. Now there's a bit of a situation with this one. We know that an exothermic energy, thing releases energy, right? Sometimes I have a bit of a challenge trying to figure out or to explain what this is going to look like. But if you remember those energy graphs, an endothermic reaction, if you're starting with reactants in this manner, they will do this. So the energy of products is higher than the energy of the reactants, isn't it? And the difference is positive. That's an endothermic reaction. So think about this graph. So it's a little bit of more integration for you here. And then, what about an exothermic reaction? You start with that high energy, and then you end up with less energy, because these ones are less energy because they released energy, okay? So here's the thing, if you're measuring the products, they will be of low energy. Why? Because energy got released when they were formed. Whereas in this case here, less energy was taken up, was absorbed into forming these products, okay? So that is the understanding. So this is exothermic. But now for here, it becomes a little bit difficult to tell what is the energy, because I didn't specify what is going on in here. Now, all you can simply say is that if you're forming more products, remember, when you form products, you release energy, right? So the idea is that if you're forming more products, then you're going to release more energy. And if you release more energy, it means the products are of low energy themselves, but there's a release of energy here. So the forward reaction should be exothermic, okay? But it's very difficult, but let me just give you a note here. NB, if you look at this, you would notice that this is a base, okay? It's a metallic carbonate, which is a base. This is an acid. So you know that acid-base reactions are exothermic in nature. So they release energy. So the other thing you can use here is to assess this, even though you know you're not in the section of acids and bases. You would know that if you're reacting a base and an acid, this is a neutralization reaction that forms a salt water and carbon dioxide when you're reacting a metal carbonate with an acid. Now this is already going to be an exothermic reaction. So in this case, you just simply say exothermic. So you have either this knowledge that an acid-base reaction or neutralization reactions are exothermic in nature. Or you can think of it in this manner, that if here you're forming more of the products, and that means when you form products, you're releasing energy. So that means delta H becomes negative, okay? Because you've released energy. You are not absorbing energy, okay? So that means the energy of the product is low compared to the energy of the reactants. And that is an exothermic reaction. So I don't know, let's not spend too much time on that. So it says explain the answer by referring to the graph, okay? Well, if you refer to the graph here, we know here that, look, the forward reaction is being favored here. I don't know, there are just too many things to consider here. Let's just answer here first. So this is 5,3.1. We said exothermic. So you have two options here for 5.3.2. Because, okay, they're actually telling you, look at the graph. Now you cannot use the reasoning that you know that this is an acid-base reaction. So they said use the graph. You have to refer to the graph. So by looking at the graph, we know that between T1 and T2, okay, maybe small letter t is better. There is more gas being formed, okay, which is basically the products, okay, the products. And this implies what? There is more energy being released as products form, okay, and therefore the delta H, or the enthalpy, is negative of the reaction. So I mean, you can say a lot of things. You can say between T1 and T2 there's more gas volume being formed, okay, maybe let's say, but if you're forming more gas volumes, that means the number of moles are increasing. So there's more gas being formed, which is products. This implies that more energy is being released as products are forming. So it tells us that the delta H is negative. So I think this tells us that now the forward reaction is exothermic. Therefore, forward reaction is exothermic. So I think that is the best explanation you can give. Again, try to be as concise as possible. Don't sing too much because they're not interested in your song. But you have clues that you can put together to now at least have an idea of what you need to be saying here. So I think this was a bit of a tricky question, honestly. Especially the fact that they didn't tell you what were the temperature changes, so that you can be able to tell. Because if they told you the temperature was decreased, for example, then you know that when you decrease temperature, the reaction that releases energy is favored, and therefore that would be an exothermic reaction. So in essence here, they've decreased the temperature for this to happen. If you decrease the temperature, the forward reaction is favored because it releases energy. But if you increased energy, you would be favoring the reverse because you need to break more bonds there. Okay, so that is the idea. And these ones will be of a higher energy, meaning you would need more energy to break them. So because they will absorb more energy to form those ones. So again, yeah, they can make this question very nice. So this question can come again, but now in the manner that we just thought of, that it can be a question of, if you decrease temperature between T1 and 2, what exactly is the forward reaction, or what exactly is the reverse reaction? So you would know that from understanding enthalpy and knowing exactly what are the energy changes when you are reacting and when you're forming products. Okay, enough is enough. So 5.4 says the percentage purity of the sample is 82.5%. Now it says calculate the value of X on the graph, assuming that the gas is collected at 25 degrees Celsius Okay, this is almost like a standard temperature and pressure. Okay, so this is the standard conditions, and you know that the volume of gas at standard conditions is 2,4 decimeter cubed. So right, I think so. Standard volume, let's see, where's our information sheet? So you always get this one, so sometimes when you forget, you just go and have a look there. What is that? So molar gas at STP is 22,4. Okay, yeah, 22,4 decimeter cubed. Wait, this is not volume, man, that is concentration. Oh, no, yeah, that's correct, per mole. Yeah, per mole, so it is 22,4. Let's see when we divide this one, but when we divide this one by what? 1000, what will it be? But anyway, let's not cause ourselves any problems. They're giving us this one deliberately, okay? Because they say take this as, so they are not giving us exactly what would be the normal situation. So this one is a little bit different from what we know. So if they didn't mention this one, you would use the molar gas volume at STP. Alright, so we want that maximum volume of gas. Okay, not a problem. So all we need now is to calculate the number of moles that actually reacted. So it is the pure number of moles here. So once we get the number of moles, we'll then compare this one, because we know 1 mole of calcium carbonate forms 1 mole of carbon dioxide. And once we have the number of moles of carbon dioxide, then we can multiply the number of moles per gas volume, which is this one. And this will tell us exactly, this will tell us the volume. Just a moment. Hello? Okay. Masu ukweza anti-hypertensive is 3 andithi. Okay, ninayo what is this thing? Captopril. So what do you have? No, it's your waiting. Yeah. Okay, sure. Okay, sorry for that, little bit of an interruption. I'm actually on duty, so yeah, so there will be a little bit more interruptions every now and then. So basically they want to calculate the value of X, which is this volume right there. So what is that maximum volume? So for us to do that, we need the number of moles first. Okay, so let's do 5.4, nice and easy. So what is the story here? We're going to do this. So first of all, we want the mass of pure calcium carbonate. So we know that the mass of pure CaCO3 is going to be what? This percentage, isn't it? Yes. So it's going to be 82,5 over 100 multiplied by what? The impure, which is 15. Okay. Now let's do that. So all you need to do is to be able to do those quick calculations nicely and easily. So what do I get? So I get 12,38 grams. Okay. So this is the number of this is exactly the grams of pure Okay, just a moment again. Yebo. So ninantoni lapha? So alinayo i-Adalette. Kanjani sister, it's an emergency drug. That it's a ward stock. Fanele kube nayo. An odd. Oh, what's here? Ilaphi ithala alinayo? Okay. It's fine sister. What I must get see observe before she act water because it's not too high at this point. So must get see observe, but if it continues, say maybe the next 3 to 4 readings are still high, then you need get a small dose here, but it's that dose maybe okay. So mhlambe siniyeze must get see running mhlambe sithi at 2 minutes per hour and then see if you are drop then we stop it. Sure. All right, so I'm being interrupted by friends. So you can see this one is much smaller, right? 12,38 was smaller than the 15 grams. So that's the number of grams of the calcium carbonate. Why am I looking at calcium carbonate? Because I want to compare its number of moles with the number of moles of the carbon dioxide gas that I'm forming. So this also implies now that the number of moles of calcium carbonate that reacted is going to be the mass over the molar mass, right? We know that, which is now 12,38 divided by calcium carbonate. Calcium is 40. The molar mass, you just use your periodic table. So this is 40 plus carbon is 12, right? Let me just be sure. Sometimes it's easy to make errors. So calcium is 40, carbon is 12, plus oxygen times 3, which is now 48. Okay, so it's 100. Okay, so we have now 12,38 divided by 100. So it gives us this 0,1238 moles. So I'm not trying to do anything silly here. So you can do 2 3 decimal places and say 2 4. It is much safer than to just drop all those and take the 2. Just leave it like that. Don't round off as yet. So we can say but 1 mole of CaCO3 is to 1 mole of CO2 gas. Okay, it therefore tells us that the number of moles of CO2 is equal to 0,1238 moles. So what do we want now? We want the total volume. So we know now for a fact that X is the volume, right? So what do we know? We know that according to the molar gas volume, it tells us that we know, of course, that number of moles is equal to volume of gas multiplied by the molar gas volume, right? No. Divide by volume of gas divided by the molar gas volume. I don't know, they write it like that. Let me just check the formula again. So at times you just need to be very familiar with okay, it's Vm. Okay, so now what do we want? We want the volume of the gas, right? Number of moles of gas is going to be volume of the gas and the molar gas volume. Okay, this tells us that now the volume of CO2, which is that we just cross multiply, is going to be equal to number of moles multiplied by the volume of the molar gas. So what did we get? 0,1238 multiplied by, they said that one is 24,000 centimeter cubed, and then of course we're talking decimeters here. So when we want decimeters, we divide this by 1,000 because we don't want, okay, let's leave it at centimeter cubed, okay, because I mean we don't really have to do anything here. So this is 0,1238 multiplied by 24,000. It gives us this one. It's 2971,2. Of course, you can make it to 2 decimal places, 0 centimeter cubed, because we were given our graph in centimeter cubed, so they wanted x, so this was in centimeter cubed. So that's the answer. Here you can say therefore x is equal to that. So this was a bit of a nice question, so a lot of things to consider. So they said 5 marks. I think here finding this percentage, I mean the pure mass and the number of moles here, and then of course eventually crossing over to the number of moles of the gas right there was cool. So here you would get the 5 marks, not a problem. So that's an easy question to handle. Now let's just try and create a bit of space here. So I hope you like this one and you know how to reason around it, okay? Alright, so that is fine. Now what are we going to do here? 5.5. It says now how, okay, let's read it together. It says now, how will the reaction rate change if 15 grams of pure, now remember this was 15 grams of impure, which only gave us 12, rounded to the nearest, it just gave us 12 grams. Now if we have 15 grams of pure calcium carbonate, it says now sample reacts with this, and then it says now how will the reaction rate change, okay? How will the reaction rate change? Will it increase? Will it decrease? Will it remain the same? Now remember, in this case we have now more of the reactive surfaces exposed, so the reaction rate is going to be much faster, okay, than when it has to look for the molecules to react with and then try to avoid those that are not. So here the reaction rate will definitely increase, okay? It should increase. Now it says here, okay, let's just write it here and say increases. So 5.6, it says now use collision theory to explain the answer in 5.5. And of course, according to collision theory, it says here, now if we're using the percentage of pure, remember we're going to increase the number of molecules available. So now with more CaCO2 molecules or particles, let's just say particles, because collision theory talks of particles, but particles are essentially molecules, okay? We can say particles or molecules with more particles. Okay, with more calcium carbonate, more particles are available for more effective collisions with HCl molecules and okay, so what am I saying now? With more calcium carbonate, more particles are available for more effective collisions with the HCl molecules, and therefore the reaction rate will increase. Okay, I think that is the best way I can put it. So it's just 2 marks. I guess here it's all about more particles available for effective collisions, and then that means the reaction rate will increase, because more effective collisions means more rate, the reaction rate increases. Okay, so this is the easy, okay, not easy 15 marks, but a bit of a challenging one. So, but again, very nice question for metric level. Okay, so that is how question 5 goes. Now let's start with another question. Yeah, maniac. So, chemistry is easier if you understand physics. I don't know what happened to the lead of this thing now, and it's going to run dry. My fear is that. Okay, found it. Now let's look at question 6 and try to chase it down too, because we've got a lot of work here. Now it says, consider the balanced equation below for a hypothetical reaction that takes place in a sealed 2 decimeter cubed container at 300 kelvins. Now usually this is a question on chemical equilibrium, right? So 2 molecules of gas P plus the diatomic a single molecule of the diatomic gas Q gives us 2 molecules of that combination PQ gas. Okay, so these are all gases, so very good ones for this. So we can see here that the forward reaction equals the reverse reaction because those arrows are equal. So now the question says define the term chemical equilibrium. So here you don't need to cram, you just need to know these things. Okay, 6.1 says chemical equilibrium. So chemical equilibrium is a state in a chemical reaction where the concentration of reactants and products remains constant. Okay, so a chemical equilibrium is a state in a chemical reaction where the concentrations of reactants as well as products remains constant. That is as simple as that. Or you can say where the forward reaction equals the reverse reaction, but that is more of what we would call a dynamic equilibrium, but that is what it is anyway. Okay, so not a problem. So we are sorted here, so easy 2 marks here. So when you understand what's going on, you just decide how to phrase the words. You use your English, which is why the language is very important as well in physics, but the simplest form. You don't want to complicate it. Okay, now they're telling us here in 8.6.2 that the amount of each substance present in the equilibrium mixture at 300 kelvins is shown in the table below. So we can see this. So let's just rewrite this because we will need to use this piece of information here. So we know that 2 molecules of gas P plus 1 molecule of this diatomic gas Q goes forward, goes backward, and gives us 2 molecules of gas PQ. Okay, it's very important. So now they are telling us that what? Okay, so let's leave it for now. Okay, now they are telling us now that the new equilibrium. So we have those initial ones, the first equilibrium. Now it says the temperature of the container is increased. So you know when you increase the temperature, what happens? The Kc changes, isn't it? The only thing that changes Kc is the increase in temperature. Now it says here, when a new equilibrium is established, it is found that, now this is a new situation, it is found that there's 1,2 moles of gas P. Remember there was initially what? 0,8. Now with 0,8 we end up now forming 1,2. So that means the reverse reaction is favored because gas P is in the reverse reaction. So which reaction is favored by an increase in temperature is an endothermic reaction. So it means the reverse reaction is endothermic, okay? So now it tells us now, is the heat of the reaction, which is the enthalpy change, is it positive or negative? The reality is, remember when we talk the reaction, we're always referring to the forward reaction. So if the reverse is endothermic, then the forward must be exothermic. And that tells us that this one is negative, okay? Because for an exothermic reaction, delta H is negative. So, yeah. So we're doing this one, 6.2 point. Yeah, man. Which color was I using, God? 6.2.1. So we know that delta H is negative. Or you can say less than 0. Why am I saying that? Because when we increased temperature, we favored the reaction that uses up energy. That means the reverse is endothermic, but we always refer to the heat of the reaction with regards to the forward reaction. Okay? So the forward reaction is exothermic, and therefore it is negative. Because you know from the graph, if you were to think of it graphically, you know that if you have that graph, for an exothermic reaction, you start with products that are at a higher energy level and then it comes down. Okay, maybe let's do it properly, because you do get a bit of activation energy and then it's like that. So you see here the energy level here is low compared to the initial, so the difference is negative. Okay, alright, not a problem. Let's not overly explain things here, we need to move. Alright. Okay, so it says now use Le Chatelier's principle to explain the answer to question 6.2.1. Alright, so it's exactly what we just said. So 6.2.2, we know that when the heat was added to the reaction, okay, or to the system, the reaction that favored the decrease of temperature okay, so we can say here when the heat was added to the reaction that favored the decrease of, okay, I don't know, man, now I'm going to do tautology here. The reaction that favored the decrease of temperature rise was favored, which is the endothermic reaction, and that was the reverse. Maybe we can just say the reverse reaction was favored, which is the reaction that favors the decrease of that temperature. And that means more reactants were formed. This implies that more reactants formed than products. Alright, so not a problem. So I think that is what we know, because it started off being that small and then all of a sudden it's bigger, so we're forming more of the reactants than the products. Again, here, if you understand how it works, so Le Chatelier's principle says if a system is in equilibrium and a disturbance is introduced into that system, the system will shift so as to cancel the effect of that disturbance. And we can see here that the disturbance is the temperature here. We increased temperature, then the reaction that cancels the increase of temperature was favored. Right? And therefore it tells us that, okay, we are favoring the reverse reaction. And the reverse reaction is endothermic because it consumes heat. And for that fact, the delta H of this entire reaction, because whenever we do a reaction, we are trying to form products, right? Not reactants. So it becomes negative because the energy of the product is smaller than the energy of the reactants. All right. Not a big deal. And we get our 3 marks here. I don't know why they're giving 3 marks. 2 marks is enough there. Anyway, not a problem. So it says now, calculate the equilibrium constant at 350 Ks. All right. I should have written this one a bit more down. Okay, these are some of the big questions where you have to calculate the Kc. So 6.2.3, we know that 2p gas plus q gas goes forward, goes backward as 2pq gas. Okay, so initially, the initial number of moles that was there, okay, because they gave us the amount. When they say amount is number of moles, initially that was the first equilibrium at 300 kelvins, sorry. So for this one we had 0.8 moles, and then for this one we also had 0.8 moles, which is strange, right? Yeah, but it doesn't matter. And then here we had initially 3.2 moles. Remember, this is number of moles. Maybe let's write it n here. N initial is like that. Okay, now we're going to have here either n used or produced. Okay, this is the section that is the most important because it tells you a lot about what is going on. But now let's say now n at equilibrium. Now this is the new equilibrium, right? Now we were told that we had gas P as 1.2 moles. All right, so we don't know what is the number of moles of this one, but we know that 2 moles of this one reacts with 1 mole. So we'll just divide that by 2. Okay, so 1.2 divided by 2, rather this is now 0.6. Okay. Oh, no, wait, what are you doing? It's dangerous. Don't do that. Okay, so now we need to know how much did we form. Here we didn't use, but instead we produced, right? So it's going to be the difference between the two. So it's 1.2 minus 0.8, right? Because this minus that will tell us how much we formed. So we actually formed 0.4. Okay, so we formed 0.4. Now this is the critical step because this is what we will use to compare now with the other side before we get to this one. So if we formed 0.4, how many of this did we form? So 1 mole reacts with, 2 moles reacts with 1 mole. So we're going to take half of that for the next one. So this one becomes 0.2. Okay, so we need to be able to work this out. And then this one forms the same number of moles, right? 2 moles of this forms 2 moles of gas P. So that means we'll still have here 0.4, okay? Because that's the relationship we're going to use. Then now let's see, at equilibrium we're going to have, for this one now it's going to be 0.8 plus 0.2. So when this is 1 mole. Okay, That is the amount of equilibrium. This is strange, so this is 1. Okay, and then this one, it's going to be 3,6, right? Wait a minute, this is a difference, right? Because we started with that one and we're going that way, so it must be the difference, not the addition. So 3,2, I almost got caught out, minus 0,4. It gives me 2,8. So remember, we're going backward this time around, so that's why you're going to subtract instead of adding, okay? Because we are decreasing now this side and we're forming this side, so here we add. So whenever you're going that way, then you will add on that side you're going to, and you'll subtract from the side you're coming from. And if we're going that way, we would add on the side we're going to and subtract from the side we're coming from. So now what do we want? Equilibrium concentrations. Equilibrium concentrations here is going to be 1,2 divided by, they told us the volume is 2 decimeter cubed. Am I right? Yes, they told us that it's 2 decimeter cubed, so that's what we have over there. And then here it's going to be 1/2, which is just simply 0,5 mole per dm cubed. And then here it's going to be 2,8 divided by 2, which is what? So this is 1,4 mole per dm cubed. Right, not a problem. Then this one is 1,2 divided by 2, which is 0,6 mole per dm cubed. So those are the concentrations. And remember now Kc, therefore our Kc is going to be, of course you will still consider this as the product, because the way you read a chemical equation is from left to right. So it's going to be PQ, you square brackets here, over P squared times that one of Q2, but that one is like that. So let's do this one. So this is 1,4 squared divided by 0,6 squared into 0,5. Alright, so let's see what is the story here. 1,4 squared divided by 0,6 squared into 0,5, man. So what do I get here? Why am I getting a strange number now? Yo. I'm getting 10,9. Hi, it doesn't sound right. Is it? Hi, when? I go ngemele. Hi, when? What is that? What is that? Is that true? Why is it so big? Did I do my calculations right, Bafwit? Let's say, okay, we got what? 1,2 of gas P. So 1,2 minus 0,8 is 0,4, right? And then 0,4 here, we know that 2 moles of this react with 1 mole, so this one becomes smaller. So we divide that by 2 and then we get 0,2, right? Great, which is that. But this one produces 2, okay, or that one produces that one, so it will be the same. So that one is going to be 0,4. And then we take 3,2 minus 0,4. It becomes 2,8, okay? Those are the amounts at equilibrium. And then now the concentration is per volume. Alright. So 1,2 divided by 2 is 0,6. That's fine. And What else do we have is 0,5, and then 2,8 divide by 1,4. What are you doing? Divide by 2, man, is 1,4. Okay, that's fine. And then this one squared divide by that one, 0,6 squared into what is that, 0,5. But you know what, here the trick is knowing how to put things together, because sometimes we make an error of not using our brackets completely well. Because why is it so big? Now for me it tells me that something is wrong. Hey, it is the same answer. I am going to take this one to 2 decimal places is 89. I'm going to take that one, so I'm getting this one. So it looks big though. I don't think I like the idea of that answer, but it is like that. It is like that. So we did our equilibrium constant. So what is the story here? So how many marks are we going to be using here? Okay. So 8 marks. Yeah, there's a lot here. So first off, this one, correct substitution and the answer, okay, is pretty easy. And then of course determining these concentrations is very important, okay. So we have 6, 1, 2, 3, 4, 5, 6, and then this one was given, so you're not gonna get a mark for it, but for getting these two you get your 8 marks. Yes, it's as simple as that. So always kill this thing when you see it, okay? Please kill it. It is not correct not to kill it. Okay, let me just go to the loo for a second. So we are doing fine. Just hold on. Oh, okay. It's a bit, I don't know how to pause these things and then continue and stuff like that, so I'm just going to be the guy who wastes time, because I don't know where's the pause button in this thing. Anyhow, we are done with this one, so maybe we just need to do one more question and cut this video, because I think it's taking longer than I wanted it to, right? But I mean, we are just an hour, so we can do a bit more time on this one. So that's all right. I like this method. So I mean, you have plenty of options, you guys know. So my method is prefer this one. Okay, let's answer the next question. It says now, how will the equilibrium constant calculated in 6.2.3 be affected when the volume of the container is decreased at constant temperature? So remember, if you don't change the temperature, all you're going to just do here, you will just shift these volumes about, because these are gases. When you decrease the volume, what are you going to do? Now you're thinking about it, there's about 3 moles here against 2. So when you decrease the volume, you're increasing the pressure. And now the pressure here will be more than this side. So the side that has less pressure will be favored. But again, it will reach equilibrium. So in totality, when that system reaches equilibrium, the Kc remains the same, because forward equals the reverse, isn't it? Although you will favor the forward reaction initially, but eventually it will get to the same. But here's the thing here. Only temperature affects Kc, so it will remain the same. Remains the same. So that is the answer. I'm going to underline this one. Give a reason. You can just say only temperature affects the value of Kc. You are done. Just trying to save time now. Losing my interest in saying a lot of things on paper, but you have all the time. Now it says, okay, more Q2 gas is now added to the reaction mixture, again at constant temperature. So if this is the case, Kc is not affected, okay? It says now, how will each of the following be affected? Choose increases, decreases, remains the same. The yield of PQ, okay? So the yield of PQ will essentially be favored, so it's going to be increased, okay? It will be increased because we are adding Q2, so the reaction mixture will form more of that one. But it doesn't mean that if you're forming more of this one, there's going to be, once this system reaches equilibrium, you will have the same equilibrium constant, okay? Okay, so it will just shift the amounts, but the Kc will remain the same because they are all in proportion. So what will it do? It will increase here the yield. Remember, the yield is the product of PQ. So it increases. It increases, or is it increases? Alright, that is Le Chatelier's principle right there. But Kc, remember, as much as the yield increases, this one will decrease in such a proportion that eventually when this is in balance, the Kc remains the same. So do not make these confusions. So this is why I like physics and maths, because these two subjects are dynamic. You need to be, that dynamic individual in your thinking. So be able to separate the points for you to make certain conclusions, but there are some very blurry lines which can leave you confused. The number of moles of P. Now if you're forming more of this one will decrease, right? Right. It will decrease. So that sums up this 18 marks, okay? I think the challenge here is often in this question where you have to calculate Kc, but usually the rest of these little questions, which are always there, you have to understand how chemical equilibrium works and how to apply Le Chatelier's principle, which is pretty easy. The tough one is usually this one, Kc calculation. But it's not really a too difficult question, but it's challenging for most. It sure did challenge me when I started learning about chemical equilibrium, but by the time I did my media exams, I had found this method here, because I think my book, which was that, remember the Study and Master of 2003, I think, but I think the book was written in around 2001 or 2, but somewhere there, but I bought it in 2003. That older book, so it was using this method. I couldn't figure it out though, because it was never explained in that book, but eventually when you started using stoichiometric calculations and thinking about what is going on, it became easy that, oh, they were doing that, and it kind of made life easy. Okay, so I don't know what you want. Now let's go to the next big one. So we're going to do the next big one, which is acids and bases. So another favorite question, because it has a lot of stoichiometric calculations also. Now we're told sulfuric acid or acid H2SO4 ionizes in 2 steps as follows. Step 1. In water it forms this hydrogen sulfide ion plus this oxonium ion. They call it an oxonium ion, or some people say hydronium. I don't know, man, but kind of got attached to the so-called oxonium ion or hydronium. Yeah. Now it tells us that now its ionization constant, which is more like Kc, right? Because it's going to be this guys over that guys. It is 1 times 10 to the 3, so it's 1,000, right? And then this one will also further ionize in water because we know it's a diprotic acid into the sulfate ion plus another hydronium ion. But you can see now that the ionization constant is much smaller, which is essentially the Kc here. So the Kc, or whatever you want to say, is much smaller than that. So what does it tell us? It tells us that this one ionizes incompletely. This means this one ionizes incompletely compared to that one. Alright, and not a big deal. Now it says define an acid in terms of Lowry-Bronsted theory. Well, according to that guy, Lowry-Bronsted says it is a proton donor. Proton donor. Okay, maybe not donor, but donor. Donor. Hey, Donna. So it's a proton donor, okay, which is this positive hydrogen atom or ion. So it's a proton donor, that's all. You don't want to say anything else. So you walk away with the 2 marks already there. It's a proton donor, but according to Arrhenius model, it says it is a substance that releases hydrogen atoms in solution. Okay, so that's all. So I mean, it's more or less the same thing, but Lowry-Bronsted says this one donates rather than to say it releases. Okay. Alright, so write down the name or formula of the substance that acts as an ampholyte in the above equation. Okay, an ampholyte is a substance that acts both as an acid or as an what? Or as a base. So look at this formula here. This HSO4 minus can accept a hydrogen from here and give us hydrogen sulfate, or which is sulfuric acid anyway. At the same time, it can donate this hydrogen to water to form another oxonium ion. So you see it can act both as an acid it can act as a base or as an acid. So that is HSO4 minus aqueous solution. So they said you can write a formula or the name. So I'd rather write the formula because I don't know what to say about that name. I'll just say hydrogen sulfide. Okay, give a reason for your answer. Well, it acts as both a base and an acid. And then of course you can state, if you like, that in reaction 1 it acts as a base, and in reaction 2 it acts as an acid. So but I mean, this is an innate character of ampholytes. It acts both as an acid or a base depending on what it's reacting with. All right, now again you walk away with your 2 marks there. Easy. So I'm answering on the paper now. I'm getting tired. The conductivity, what is that? The conductivity of solutions of this ion and the sulfuric acid in solution are compared. Now, which solution will have a lower conductivity? Now, what is conductivity? When you talk of a conductivity, remember these substances are ionic when they dissolve, isn't it? Because look at sulfuric acid, it dissolves in water into ions, and these ions can conduct electricity. So basically conductivity is the ability of a solution of a particular substance to conduct electricity, okay, when a potential difference is put, okay. No problem. So now you can tell here, this one ionizes almost completely here because it's much more, so it has a higher ionization constant. And that means if it has a higher ionization constant, it will have a higher conductivity because it will conduct electricity more than this one. So basically here the answer is, well, this and compared, which solution will have a lower conductivity? Again, we're saying it is the solution of the HSO4 minus. Why? Because it has a lower Ka value. Why do you need to say too much? You just say that. Or you can say it ionizes incompletely. So its equilibrium lies far to the left, not to the right, okay? Alright, so I mean, easy 3 marks there. Not a big deal. So there the power goes. Whoa, but at least my camera is a little bit full, so I'll be able to complete this lesson here, I hope. Maybe we can cut this one into 2 sections, maybe to the last one when the power comes back. I hope it will come back. Anyway, so we are almost there. So now the question says the pH of a hydrochloric acid solution is that one. Calculate the concentration of the HCl solution. So if we're given the pH, we need to find the concentration of the HCl. Now remember the concentration of the HCl, because HCl ionizes completely. It will give us exactly, it will be exactly the concentration of the oxonium ions or hydronium ions. So this one we demand, it demands a writing. So we tried to save a bit of time, so let's try and move. So 7.2, we have a situation here where we have HCl in solution. We know that this can go into what? Into the oxonium ions. I mean, remember here you just add water if you like. So you're going to have here Cl minus plus H3O plus. Or you can just write H plus plus Cl minus. I mean, it's up to you how you write this one, but you just ignore the water because you know this is in solution. That is the aqueous solution there. So that tells us that if we find the concentration of the oxonium ions, we've essentially found the concentration of the acid because it ionizes completely. It is a strong acid. So now we are being told that the pH is 1,02. Okay, so they want the concentration, but now what do we know? We know that pH of any solution equals minus the log of the concentration of the oxonium ions. Alright, now we know that, well, this implies what? We were told that the pH is 1,02 equals, well, now we can use logarithms, isn't it? Logarithm says if this is negative, this, now we use that, the exponent will multiply the number, so it's going to be to the minus 1, isn't it? So a bit of mathematics there, which also implies that 1,02 equals log, we change this now using exponential rules, it's going to be 1 over this concentration of oxonium ions. So you see a bit of mathematics right there. So now for us to solve this, we need to convert to exponents. This implies now what? That this guy right here, now remember the base, when it's not written, it's always 10. So the base comes and pushes that to where it should be. So we know that 10 to the exponent 1,202 equals this situation over here. Okay, that's when you're converting to logs. Right. Now what do we need to do? Remember, if you have fractions, then you may as well do fractions. So what we're going to do here, cross multiplication. So a little bit of mathematics, I tell you. So this one there, and then this one there. Okay, so maybe let's just do it. 10 to exponent 1,02 multiplied by the concentration of the oxonium ions or hydronium ions equal to 1, because 1 times 1 is 1. Therefore, the concentration of the oxonium ions, I'm just prolonging this so that you can see how to do it. Otherwise, I could have really gone easy on myself already. It's going to be 1 over 10 to the exponent 1,02, which is that one. 1 divided by 10 to x. Hey, when it's can't get usual 10 to 1,02. Okay, so what do I get here is 0,095. Okay, 0.95. Maybe let's make it 5. Okay, because it's quite big numbers there. Of course, you don't want to round off too soon, so the bigger the decimals, the more the decimals after, the more accurate you're going to be when you round off to 2 at the answer. So this is mole per decimeter cubed, isn't it? Because that's the concentration. But now we know here, well, Lord, what are we going to say now? So, Ahmed, we can say, but one concentration of HCl produces one concentration of oxonium ions. Yeah, therefore, the concentration of HCl is going to be that one, 0,09. If you do 3 decimal places, let's just leave it at that, 55 mole per decimeter cubed. No need to complicate our lives. So that is the answer, eh? Yes, that is the answer. So I made it longer. I don't know why. Yeah, sometimes it happens that you prolong the inevitable. But that was just 3 marks. So critical was getting this guy, and then this guy. And then you see this conversion. I think this conversion here, eventually, I don't know, man, there's just a lot to think about here. Maybe because all of this is a mathematical gymnastic, I prefer to say to you the correct substitution over here. Let's just mark it here if we like, so it gives us the 3 marks. The rest was just mathematics, and we are not really trying to do maths, but we're applying it, so you won't get marks as you would when you're doing a maths question like that. Alright, so that was 7.2.1. Great. Easy 3 marks, really. Nothing serious there. Then let's go on. What is the next one? It says now, this HCl solution, this one with that concentration, reacts with sodium carbonate, like that. So this is sodium bicarbonate, right? Okay, not bicarbonate, but sodium carbonate, according to the following balanced equation. Again, this was, I feel like you guys are being spoon-fed though. For you to do chemistry, at some point they need to just give you names and not even the formulas. You need to be able to form those reactants first by knowing their chemical formulae, then do balanced chemical equations. So I don't know why they make it so easy. Why? You need to know how to form these reactions so that you can become sharper in the laboratories when you start forming new compounds. Because if you have not been told, then you're not going to be able to figure it out. So that means you'll always have to be told what the chemical formula is like. Then how is that research of yours going to be powerful then? Gonna be copying others, right? Right. So no man. There are rules that are followed when these are formed, so please learn them so that you can do this on your own. Anyway, I'm wasting time by talking a lot. So there it is. So 2 molecules of hydrochloric acid react with 1 molecule of sodium carbonate to form 2 molecules of sodium, or they call it table salt. 2 molecules of table salt plus 1 molecule of carbon dioxide plus water. And you know that this is an acid-base reaction, isn't it? When you react a metal carbonate with an acid, you get salt, carbon dioxide, and water. This is something you need to know, because based on this you can now imagine what this reaction would look like. And then again, you need to know how to sort these ones out. You know that the carbonate ion is 2 minus. So if it is with sodium, then you know that you need twice that, because sodium is an element of group 1. It has a +1 charge. So okay, again another interruption. Hello. Kau seumpan mungkin lah. Yeah. It might go to many, like 2 minutes ago, 5 minutes ago, I go back. It's fine. I got a shallow stable at 2:15. So this was a massive column because until the bottom of them scared. Sure. Alright, so a little bit of an interruption again. I'm on duty, friends, so yeah, I'm being interrupted, but I felt I should push this. Maybe it will help somebody, maybe it won't. It doesn't matter really. Those who are still to write their media exams, they will be able to maybe learn something, I don't know. And if you learn something, please don't hide it from others. You can share it to them so that they can also judge for themselves whether this is useful to them or not. And if they also find it useful, please propagate to others. The idea is to reach as many people as possible. And if it has reached 2 or 3 people, for me, that's even more than enough. Because if it is able to change the state of understanding of these subjects for at least a person or 2, it has really become successful, isn't it? Yes. But it can also go for more. So the minimum is 1, right? 1 or more. It's good. Yeah. But please, folks, double check some of the things I say here, because they're not necessarily bulletproof. I want to state that. And whatever I'm saying here cannot substitute what you are taught, okay? Sometimes your curriculum has certain objectives that I may not know, because I really don't check what is in your curriculum at all. I just use what I find in front of me and combine with all that I know about the subject. So at times it's just my own interpretation, not necessarily what is there, but trust me, I do my best to stay away from just my own personal interpretations, but I try to at least combine this with what is accepted currently, at least. So I'm not going to give you too much of my opinion here, but I'll give you more of what you can find in any textbook that covers the subject. Alright, enough of that story right there. So the question says now 50 centimeter cubed of the solution. Remember now, this solution has this concentration, is being added to this volume of that with that concentration. So we are doing a neutralization reaction here, or an acid-base reaction. And what is that? What is the delta H? Yes, you said it right. It is negative, because we said Neutralization reactions release energy, so they are exothermic reactions. Keep that one in mind in case they throw in a punch at you that what is the delta H of this one. Now here your only understanding is that this, in general, they are exothermic reactions. They release heat. So when you combine these two, you'll realize that the test tube, when you put a temperature there into it, the reaction mixture actually starts rising, because when you measure the temperature of this one and the temperature of this one, you will probably get room temperature, right? But when you start reacting the two, you will see that the temperature will be much higher than the room temperature, okay? So these are some of the experiments you guys should be performing at your school labs, so that none of this is a lie. You realize that it's not a lie, it's not some theoretical BS. I'm going to say BS, but it is sometimes a reality that you can actually observe happening. Alright, so now here we know we're going to do some stoichiometric calculations, some very tough ones. Okay, let's have a look. It says calculate the concentration of the excess HCl in the new solution. Now remember, once they talk about new solution, remember now you will have to consider the volumes together. So 50 plus 25 is 75, because you can consider the volume, the concentration in this 50, but now the new solution will have yet another volume to consider. So this one is a bit of a tricky question, I tell you. But let's go and do it. Let's do it. Let's do it. Let's do it. So they gave us big hitters here. Okay, not a problem. So let's write down the equation first. 2HCl in aqueous solution plus sodium Na2CO3 also is in solution. Alright, goes forward to 2NaCl, which is also in solution, plus carbon dioxide gas, which is just going to form bubbles in there if you close the tube. But if you don't, it's going to evaporate out. Alright, plus water again. You'll see water here is liquid. So you see that's why these ones are in solution, because of this water here. H2O, not H here. What am I writing? H2O, liquid. So I just wanted to do this. This was what you had to formulate yourself for us. So the questions were even much meaner, and there were less marks for all of this trouble, There were less marks for it. So you guys are living large, I can tell you that. Alright, so this is 7.2.2. Okay, let's finish this thing. Alright, now let's look at this one. So we know that the volume of the acid is what? 50 centimeter cubed. We're just going to leave it at that for now. But we know that the concentration of the acid alone, not in combination, was the one we just found above. What was that number again? It was 0.0955. That was 0.0955. Okay, mole per decimeter cubed. And then they are telling us that the volume of the base is 25 centimeter cubed. The concentration of the base is 0.075 mole per decimeter cubed. Okay, these are very important to consider. Now I should have written this in another color because it's cluttered now. You can't separate what is what. So maybe let's use another color for the answering. For the answers, where is my colored ones? Alright, so what do we have here? Look, what reacts? Remember, if it tells us this is an excess, this is the rate limiting reagent or reactant. Now, what do we want? We want the number of moles of the base, because the number of moles of the base is exactly the number of moles of the acid that we're going to use. Okay? which helps us because the initial number of moles of the acid is going to be those ones right there. Then we can be able to tell now how many moles were left, and then we can do the concentration at the end. So now let's start here. Number of moles of the base is going to be the volume of the base multiplied by the concentration of the base. Again, you know that this comes from that formula that says number of moles is what? No, concentration basically. Concentration is number of moles over volume, right? You know, this is taken from that. So remember, don't have to cram that. You just know this one. It's in your answer. It's on your formula sheet. And then you do your thing. So the number of moles of the base here is what is going to be the volume. Now remember, the number of moles, we have to convert that to decimeter cubed. So let's just do this one already here. So when you convert centimeter cubed to decimeter cubed, again, there was a mnemonic we used to use here because it was a bit technical. So we said King Henry died a miserable death common to mankind. Okay, so basically you know that this is millimeter, centimeter, decimeter, meter, decameters, hectares, kilometers, right? Right, so you know that this was 1, this was 10, this was 10 squared, this was 10 cubed, this was 10 to the 4, 10 to the 5, this was 10 to the 6, okay? So we always had that one in mind because you know that, well, 1 centimeter equals 10 millimeters. 1 decimeter cubed equals 100 centimeters, and like that, okay? So sometimes these tools were very useful because, I mean, we didn't have much going on, but you guys have a lot of fancy things now to help you do these conversions, so it's not a big deal. So now we're going to simply say 25 divided by 1000. Alright, so which is going to be now 0,025 decimeter cubed, which is important, right? I think it's important. So it must be in decimeter cubed because the concentration is in mole per decimeter cubed. So the decimeter cubed will cancel and then you'll remain with moles because that's what you want, right? Okay. Maybe we'll have to cut this video on this one and continue later. I don't know. Alright, so this is going to be now volume 0,025 multiplied by 0,075. So multiplied by 0,075. Yo, I get a very big number, 1,875. It's not too big, so I'm going to write it as it is, times 10 to the minus 3. So that means it's 0,01875. Okay, that's what it is. So it's just written in scientific notation, moles. So these calculators don't allow you to write those big zeros. Just puts it into scientific notation, which you need to also know how to do. Okay? Okay. So what are we doing here now? What are we doing here now? We are going to say from our chemical equation, we know that 1 mole of base reacted with 2 moles of acid, okay? Therefore, or you can say 2 moles of acid reacted with 1 mole. Therefore, the number of moles of acid is going to be equal to, now this one you multiply by 2, okay? So now this one gives me 3,75 times 10 to the minus 3 moles, okay? Again, if you want to write it as a straight thingy here, it's going to be 0,00375 moles. Again, you need to know how to do these conversions. They were quite significant. Alright, so now we know the number of moles of acid that actually reacted with this one. with this volume of this, right? So now, but we can say but initial number of moles of acid was what? It was the concentration of the acid, which was multiplied by the initial volume of the acid, okay, which is V of the acid. Now the initial concentration was what? 0,095. So it's 0,0955 multiplied by the volume that was initially used was that one. So we have to convert that to decimeter cubed. So it's going to be divided by 1000. I'll show you why you end up doing that. So that is 0,05 decimeter cubed. So we're going to put 0,05 over there. Then times 0,0955. What is that? So it gives us 4,775 times 10 to the minus 3 moles. Okay. Now, therefore, the number of moles acid in excess is going to be the original, which is 4,775 times 10 to the minus 3 minus 3,75 times 10 to the minus 3, right? Now we know 4 minus 3 is what? 4 minus 3 is just 1, man. And then this one, so we're going to say 5 minus 5 is just going to be 5. Okay, maybe 0, then we need 1 to become 10, then it becomes 5. Okay, let's not cause ourselves problems. Let's not use our head. We don't have to. Minus that one. This one minus that one. 3,75 to the minus 3. Okay. It makes life easy. So we get 1,025 times 10 to the minus 3 moles. Now this is the number of moles of acid in excess. Okay. Great. Now, once we have the number of moles of acid in excess, we can say, therefore, the concentration of acid in the new solution is going to be the number of moles of acid in excess over the total volume of now this whole solution. So this one is going to be 1,025 times 10 to the minus 3 divided by the total volume. Now it's going to be 50 plus 25, which is 75, right? But this 75 is centimeter cubed, so we're going to say 75. Okay, maybe let's write it like that so that you can say it. It's 75 because it's 25 plus 50 divided by 1000, because you want it in decimeter cubed. So 75 divided by 1000. Okay, let's just be silly for a second and then see what is that. What is that? So this is 0,075. Okay, not a problem. So if 1,025 to the minus 3 divided by 0,075. Oh, sorry. So I get here 0,01. Maybe let's make it, yeah, but this is fine. I mean, to 2 decimal places, it's okay. Because normally that's the answer they want, right? This is mole per decimeter cubed. Now we can finally do to 2 decimal places at the end. So that is the end of this question. So it's a little bit of a long question. And again, I mean, there are shorter methods you can use, but I think this one makes a bit more sense and it's much easier to approach than others. As much as it is long, there are shorter ones, but you will start to have problems with them if you don't understand how they work. So let's just say finding the number of moles here is good, and essentially equating that to the number of moles of the acid. and then getting the original here is great, and getting the number of moles in excess is great. And this formula here, this substitution, and this one. So it's 1, 2, 3, 4, 5, 6, 7. Where do you get the 8th mark? Maybe here, to show that there'd be a difference over there. So you have your 8 marks, and that sums up this bit of a challenging 18 marks in that last question for sure. Alright guys, so I don't want this video to be too long, so as a result I'm just going to chop this video here and then do the last 2 alone, okay, when the power returns. Alright guys, thank you for watching, and thank you for your patience with me. I've had a few distractions. I hope they did not annoy you too much. I hope you also didn't hear those conversations I had, because my plan is to hide what I am. Yeah, anyway, so if you did hear, well, you won't really understand exactly what's going on, I know for sure, because I wasn't too explicit, right? Right. Alright guys, so I hope you like the video, and I hope you understood all the reasoning process we went through, and you were able to visualize all those calculations that we did, especially the calculations. They can be a challenge, so you need to understand a bit more. Again, please try to learn these chemical compounds, be it organic and inorganic. Be able to know how to write their formulae, their chemical formulae, even if we're not shown them. Okay, be able to write a chemical equation for a particular reaction, even if you are not given that particular chemical equation, and be able to balance it as well. That means you'll have to understand your periodic table, you will have to understand the oxidation numbers, and you will also have to understand the theory behind these sections. When you're doing acids and bases, when you're combining sort of like a metal oxide and an acid, what would you get? And what happens when you combine a metal carbonate with an acid, what do you get? You know, things like that, they need to make a bit of sense. Then you'll be able to now formulate these equations. Even in the section of inorganic chemistry, be able to know what equations, or at least which substances react together to form what, be it the sulfuric acid, which is the contact process. You need to know those equations, and even those, stepped equations, you need to know them. When you want to produce sulfur dioxide, sulfur trioxide, and then to sulfuric acid, and then of course nitric acid as well, nitrogen monoxide, nitrogen dioxide, and then nitrogen trioxide, is it? No, nitrate ion or nitric acid, yeah. And then again, what was the other one? Is it the contact process for sulfuric acid? And then it is the nitric acid, what is that called again? Ostwald's process. And then the Haber process for the production of ammonia. You need to know those things, because any one of them can be brought to you, either in the chemical equilibrium type of a question, or wherever they find the joy to put it. The other ones you need to know for these kinds of calculations, know those formulas, be it percentage purity, the relationship between the concentrations and number of moles and molar masses, how these moles are compared in a chemical reaction. This many moles react with that many moles of the next substance, and all of those things, they come together and give you some sort of comfort in answering these questions. Before I sound a little less mysterious, I'm going to cut this video here, and then see you in the next video when we finish up this paper. I hope all these videos will find you well in time, so that you can be able to use them to sort of revise passively, I guess, because you don't really have to write anything down at this point in time because it's already injury time. Okay, you can just sit there and watch these videos when you have completed your revisions, your practices. Now when you feel like you just want to seal your practice, I would advise that you maybe watch these videos at that time when you've already done your part with other questions that you have, or even these ones, doesn't matter. But when you feel like you've practiced enough, you've reviewed your notes enough, and you feel like there's nothing more you can do for yourself at that point in time, then perhaps sit back now and watch these videos and see if you remember most of the things that I go through, and see if you follow. And when you feel like no, I'm not following, pause the video and try it out yourself, and then listen to the video and see if it makes any sense. And I think that's the best way to really get a better scoop out of that exam tomorrow. Otherwise, see you in the next video. Thank you for watching. Please share if you can, and maybe like the video so that it can reach as many people as possible as well. And if you have any queries, you can put them in the comment section or email them. Bye bye.